Anyway, I'm here today to try to address this question and see whether my answer can be the correct one. In terms of, I like to sort of guide you through the fact of why we are using accelerators and what we have learned so far, and a little bit use the big discovery which we have announced in 2012 of the Higgs boson as an excuse for telling you where we stand and where we are going. So, fundamental research. Probably I should not spend time explaining this to you, but let me just remind you what is fundamental research the way we see it. It's basically that intelligent humans have been asking simple and profound questions since the very early times. So how did the universe begin? What is it made from? What are the fundamental laws which are regulating its functioning? And in fact, modern physics, I mean the modern physics which we do, is actually trying to address these questions. So this is basically, the idea is basically to try to figure out what are the fundamental building blocks of nature. And here is a little bit of the evolution of our understanding. I mean, starting from the atoms, which was really found in the 18th century, but then the fact that we realized that it was composed by the nucleus, and we've always been trying to explore deeper and deeper. Then the nucleus is made out of protons and neutrons. There are electrons going around the nucleus, and in fact, in the 70s, we discovered that even the protons and the neutrons were not elementary, but they're made out of quarks. This is, if you like, is the global picture, which basically can represent anything which we can touch, which is around us. Now, besides trying to understand which are the fundamental blocks which are building our universe, we are also trying to understand which is the cement which keeps these things together, I mean, the fundamental forces. And here you can see we have basically found that all which we can observe can basically be explained by the existence of four forces. The two of them we are very familiar with, in the electromagnetism and the gravitation. The others are the one which basically regulate the way the nuclear world behaves. The strong forces which are responsible for keeping the nucleus and the protons together, and then there's the weak force which instead explains the radioactive decays and if you like, is at play in nuclear power plants or in the way the sun functions. The other point is, which I presume most of you are also familiar with, is that the way we represent forces is always in a certain form, in the sense that when I exercise a force, I mean, here I'm basically transferring energy from me to the glass, and so this is the vector of this force is basically my arm. And for every of the forces, we have as well fundamental particles which are actually transferring this energy and momentum from one particle to another. The strong force is the gluon, the electromagnetic force is the photons, the weak force are three bosons, which we call W plus and minus and Z. And for what concerns the gravitational force, we presume there's going to be something which is similar, I mean a vector, which is called graviton, but we have not seen any yet. In fact, gravity is one of the mysteries which I will be talking to later. Now, what have you understood so far in terms of how the nature works? Here you can see some sort of the table of the elements, of the fundamental elements of nature, as of the 3rd of July 2012. These are the two quarks and the electrons, which basically explain basically all of the stuff which we see around us today. On the other end, we had started understood already rather early on looking at cosmic rays and studying the cosmic rays that we had additional particles, additional quarks, like the strange quarks. We had a heavier brother or sister of the electrons, and also there were these funny particles, which are the neutrinos, which need to be, which were introduced in order to explain how the various other particles were decaying. And then basically these are the four families of particles which basically transfer force. And with accelerators, we basically by always using the E equal mc square, where basically with accelerators which had become more and more powerful, so basically being able to put in the game more and more energy, we have been able to study also other state of matters, which are leading to this picture, which is that we have three families of particles. The group of particles which are basically responsible for transferring the interaction and the forces, and all of this in fact is the domain of the studies which we do with accelerators. The accelerators have allowed us to, if you like, to study with deeper and deeper understanding and improved precisions how all of these zoo of particles behave. One of the questions which we have not yet an answer to is, for example, why there are only three families, or if you like, why there are three families at all. Now, to be noticed that gravity is always outside of this box, because basically every effort done until today has failed in integrating in a coherent picture. In the coherent picture, in a coherent model, for us, a coherent model means a mathematical representations of things. The gravity together with the rest of the stuff, even though the gravity is very real and it's actually fairly well understood as a force. Now, let me move on to another thing, which was a big puzzle. Once people started putting everything together and they kept discovering this diversity of fundamental particles, one thing which people were failing completely to introduce into the models were an obvious fact. These particles, some of them were massless, but most of them had a certain mass. They had actually different masses. And in fact, here all of the circles are proportional to, if you like, to the mass to the relative mass of the various particles. This is the protons, and you can see the top quark is the heaviest one. Then there is the Z bosons, the W bosons, the B quark, the C quark, the tau quark. The electrons is these little tiny things, and even recently we even discovered that the neutrinos, which were thought to be massless, have a very tiny mass. Now, all of these, the diversity of it, and the mass per se, basically we did not understand in the 60s, when people were trying to put these all things together, or even in the 70s, up to the 70s. In fact, what it meant was basically if you try to put the mass into the equation which we're trying to describe the model, the whole thing would fail. I mean, the mass would fail. You start to do the equivalent of dividing by 0, which simply meant that there was something which was missing in the model, of course. It's not that because the mass existed and people, I mean, every morning when I wake up and I weigh myself, I realize that mass exists. Anyway, this thing was solved by a bunch of guys which basically had the right idea. And in fact, it was a triumph of quantum field theory, which is the introduction of the Higgs field. If you go back, let me do some little bit of history. If you flash back to the 60s, the success of quantum field theory for the electromagnetism was failing to easily extend to other interaction. In fact, one of the problems was this one of the mass. Alternative approaches became fashionable. People were talking about S matrix and Reggie Pauls. And I actually, when you look at the literature, there were 2, 3 or 4 places in the world which were still continuing to work on quantum field theory. All of the others were moving on to the fashionable theories of the time. Now, all of a sudden, in 1964, 3 papers appear which propose a solution to the problem posed by the, if you like, by the fact, the way they were trying to explain was that the short-range of certain interaction, like the weak interactions, were implying that the bosons, which was transferring energy, was at large masses. These guys were Higgs, Englert-Brout, and Guralnik, Egan, and Kibble. Now, these three papers remained almost unnoticed and almost ignored until they were integrated into a proven visible complete theory, which were in fact the electroweak, which we started with Glashow, and it was basically eventually brought to its completion by Weinberg and Salam in 1967. So it took some years. In fact, it took even some years for the theory of these guys to become established. By the 1970s, people were convinced that the problem of the mass was solved, and we had a complete theory. And the quest for the Higgs boson started. Now let me tell you what is this. Now, in fact, let me walk you through what these guys did, because it's somehow, I consider it a revolution. Because let's think about elementary particles. Elementary particles evolve in space-time, because whenever you try to describe this motion, is basically by the space-time, by the equation which are their behavior in space and in time. So, let's think, what becomes of space-time if you take away the elementary particle? So basically, it's vacuum. There's nothing, there's a vacuum. So vacuum, if you like, is the fabric, the tissue of space-time. And how do you imagine this vacuum? And in fact, which is a natural way of thinking. This is the way the whole even the physicists at the time were thinking about the vacuum. The vacuum is basically empty. It's without matter and without energy. In fact, that is, in every point of space-time, the energy is null. That was the underlying assumption, that people, if you like, the potential is trivial. Now, in fact, Englert-Brout, Higgs, and Kibble, and Guralnik, and Egan basically questions this assumption. What happens if in every point of space-time the fabric becomes non-trivial? They introduced a non-trivial fabric. In fact, in every point of space-time is characterized by the presence of a field which has a non-zero potential. In fact, the way things was being imagined was that in the universe, at the beginning, it was extremely hot, and while it was expanding and cooling down, all of a sudden, the potential of the vacuum went from something trivial to something completely non-trivial, in the sense that the potential took this shape, and the most favorable place where the universe could be was not at zero potential, but at a non-trivial, non-zero potential. Now, in fact, this basically meant that, you know, whenever particles in this field would basically try to move, I mean, they could move like this, and this is, if you like, the photons, which is basically zero mass. But if they try to move in another direction, they would basically feel a resistance. They would basically start feeling something which was basically opposing to the motion. Now, F equal ma. I mean, the thing which tend to oppose to the state of motion of a particle is the inertia, and it's creating inertia. It is the mass. And so basically, the mass was naturally, to a certain extent, introduced by having this kind of potential for the vacuum. Well, it's also that the symmetry of the vacuum was broken, and so this is called typically also spontaneous symmetry breaking. In fact, there's also non-trivial. This thing basically it could be considered a mathematical artifact, which basically allowed to introduce to put the mass into the equations and not have them break down. On the other hand, there was a non-trivial prediction, in the sense the excitation of this field, the radial excitation of this field, predicted the existence of a particle, which, if you like, was the boson, which was the typically associated to this field. And in fact, in these three papers, the reason why it's called the Higgs boson is that Higgs was the only one which in a footnote of the paper remarked, and he said, well, if the field is like this, of course there's going to be a new particle which corresponds to this field. The other two papers, the guys of the other paper, when interrogated about this, they said it was so obvious that we didn't even mention it. Well, they made a mistake, because now it is called the Higgs boson. Now, once you do that, I will not go through the intense mathematics here, but this is a standard model, if you like. This is what these Higgs, what was the conjecture of these guys, added to, if you like, to the fundamental Lagrangian. And if you like, this is the description, the mathematical description of our universe so far. Now, if you manage to do the calculation for complex system, you could basically derive everything from this. Let me actually share with you as well the fact that this mechanism is also is probably deeper than just explaining the mass, because basically, when I'm sure you have heard about the Big Bang, which is this thing which basically is the model which represents the origin of our universe, starting from a singularity, and then all of the things started expanding in the Big Bang. But in fact, in the Big Bang, the one thing which was always missing was the banging mechanism. When you look at it, I mean, the standard Big Bang cosmology requires that the bang to be somewhat special. When you look at the uniformity of the microwave background, if you like, when you look at the temperature of the universe as measured over the whole extent of the universe, you see that it's incredibly uniform. Now, don't be fooled by the color coding here. The scale of the colors goes from minus 200 microkelvin to plus 200 microkelvin. So the whole universe temperature is uniform at the level of 400 microkelvin. 0.4 per mil of a degree. So it's incredibly uniform. In order, and here in the universe, you have zones of the universe which cannot talk to each other. So the only way where you can explain this uniformity is, I mean, to reach this kind of equilibrium, if you like, is that at a certain moment, this whole universe was coming from a volume where things could be uniform, could be considered uniform at the very beginning, and then it expanded so brutally that this uniformity could not be destroyed. In fact, in order to explain this you have to believe me, is that one has to have an exponential expansion with the time constant of 10 to the minus 38 seconds. It must be one of the most brutal explosions ever seen. Such expansion had to be provoked by a mechanism providing, in fact, an horrendous negative pressure to counteract the gravitational attraction, because in the universe at the time, even if it was very small, there was all of the matter that we know today, all of the energy which we know today. So, again, the guys who basically found a mechanism to explain this brutal expansion in 1982, these three guys, found that such negative pressure could be generated if the universe potential at a certain moment, while the universe was cooling off, went from a certain potential down to a more negative one. And in fact, while the universe is rolling down, one can actually generate this sudden expansion. Now, if you look at the shape of this thing, it's actually not so different from the Higgs potential. So studying the Higgs potential might actually lead to much deeper understanding than just the mass. Anyway, let me now come to the tools which we are using. Why we use accelerators? Accelerators are in fact, what they do is to accelerate particles. And to be used, I mean, the fact that these particles, then which have increased, which have their energy increased, are used as probes to either generate new particles by energy conversion, is the famous E equal mc squared. Basically, once you play in a collision, you put in play a certain amount of energy. Well, c is the speed of light, so it's a constant. You can basically generate any object which has a mass which is below the energy which you are putting in the play. And that also, the other thing which is also important, is that you can explore the space-time structure of the fundamental interactions, because basically, if you like, the distance at which you can probe what is happening is actually inversely proportional to the energy, or if you like, conversely, the time, the time intervals on which you are trying to explore the dynamic behavior of forces is actually as well inversely proportional to the energy. So by accelerating particles and studying what happens when these particles interact, you are basically either producing new state of matters, or you are studying how the forces which act in between these different state of matters are more and more precisely. Now here I have in order to achieve this, you need a tool which is basically accelerators, and I have a small movie just to show you how the accelerator we are talking about today, which is the Large Hadron Collider at CERN, works. Now let me see if I manage to get to the point of to start this little movie. So this is, in fact, is one of the magnets which are basically forcing the protons which are being accelerated at CERN to go around the circle. And okay, let's follow a proton along its path. I mean, here's a proton with these 3 quarks inside, and here there's an emulation of a radio frequency field which basically accelerates it. And we have a set of 4 different accelerators which in turn accelerate more and more of the protons. There are protons which are then on the circular ring. There are protons going in one direction, protons going in the other directions. In fact, in order to make the process economical, protons are very small. It's very difficult to make to aim one proton to another proton. We put a lot of them together. We put them in packages, in packets, and each packet contains up to 170 billion protons, and there are 2,700 packets which are circulating around the accelerator. Now you can see the proton with all of its companions is going one way, they go in the other way. And then in the point where the 2 packets collide, we basically put our detectors, and this is basically an outline of the CMS detector. And apart from the animation, what you will end up seeing here, this was basically developed in 2010 when we saw the first collisions of the LHC, and this is actually one of the first events seen by CMS. And of course, it is represented, all of the traces represents all of the reconstructed particles which were coming out of the interactions as seen by computer, of course. So this is the tool for, one of the fundamental tools for discoveries is the accelerator. And in fact, this is the LHC at CERN. You can see this is the Geneva Lake, there is the Geneva Airport, somewhere here. Geneva Airport, here I can see. When I move it here, it doesn't move there anyway. So there is the Geneva Airport. Here is the lab, the CERN lab. And what you cannot see when you land into Geneva is this yellow thing, which is a 27 kilometers tunnel, which is roughly 100 meters below ground, which houses the accelerator. The main component of the accelerator are these magnets, which are superconducting magnets. Superconducting dipoles, which basically keep the protons on the circular orbit. Now, these protons are basically colliding in 4 points around the ring, and these 4 points we have our detectors. There are 2 general purpose experiments, CMS and Atlas. Today I'm going to talk about CMS, given that it is the one which I know better. And then there are 2 specialized experiments. One is called LHCb, which basically looks at studies specifically all of the aspect of final states which contain the beauty quark, and the other is Alice, which is more dedicated to very specific runs, which happens once a year. Out of the 11 months with the accelerator runs every year, 1 month is dedicated to accelerating not protons but heavy ions, typically lead ions, and then one studies what happens in the collision of lead and lead. Now, as I say, one tool for discovery is the accelerator, the other is the experiment, and this is the CMS experiment is an artist view of it. Just to give you an idea, this is the size of a man, and what you see in the experiment, there's basically many different layers. There's a tracking layer, and then there are layers outside we call calorimeters, which are helping to identify the kind of matter fragment which are flying out, which are being traced by the tracking. And then all of the thing is embedded in a magnetic field, which allow us to do the measurements of the momentum of the particles which are coming out, and the whole thing is in the return yoke of the magnetic field. We have chambers which are basically measuring the particle which managed to get out of the dense part of the calorimeter, which are typically muons. Now this thing is basically 14,000 ton. It's 26 meters long and then 14 meters in diameter. So it's not a small thing. And this is a photo taken last year, a fisheye photo where you can see the detector was open, and you can appreciate the extent of the central solenoid, which provides a magnetic field. This is one of the largest solenoids ever built. It's 12 meters long, 6 meters in diameter, and it provides a field of 4 Tesla. Now, let me move on now on what was the kind of events which we saw and which led to the discovery of the Higgs particle, of the Higgs boson in CMS. I mean, the one thing that the theory can tell us, could not tell us, was what was the mass of the Higgs particle, but we could basically predict how the Higgs particle, which is a very ephemeral particle, it lasts only for 10 to the minus 24 seconds on average, and then it decays, it disintegrates, and the way it disintegrates is very well predicted by the theory. In particular, it can disintegrate into 2 Z bosons, each one of them as well very short-lived, which basically decays in turns into, can decay into 2 muons or 2 or 2 electrons, for example. So we were looking for this kind of topology in the final state. You have to realize that the probability to produce a Higgs boson, I mean, the conversion of energy into mass is a very democratic process. Anything which has a mass below the energy which we put in play can be produced. What is different is the probability of producing one particle or another. And in fact, the probability to produce a Higgs boson in the 2 proton collision is in fact 10 to the 10 times smaller than to produce any other final state. So the choice of the decay channel determines in fact the signal of a background ratio and the mass resolution. There's necessarily a background, because some of the what is produced in the collisions resembles naturally to the topology which you are trying to look for, and they also sometimes there is basically inevitable to have this kind of background. And in fact, in this specific case, we are very proud of this plot, because this plot was used by Olga Botner to exemplify what the Higgs boson discovery meant when they gave the Nobel Prize in October 2013. And you can see here, as a function of integrated data, while over the 2 years where we took data, you can see the build-up of background. These were, if you like, the blue things is what we were expecting. This is, if you like, is a single Z decaying to 4 muons. Or this is, for example, the production of 2 Z bosons naturally, without necessarily coming from the decay of the Higgs. And you can see that what we were observing was matching what we were expecting, except for an accumulation of data at around 125. This is the unit which we use for the mass and for the energy. It's called the giga electron volt. And once we basically reached a level which was telling us that this was not compatible with the statistical fluctuation, we felt that we had a discovery, that we were seeing something new. Now, the other thing was, we got even more convinced once we started thinking, I mean, the Higgs can also decay, the Higgs boson can also decay into 2 photons. And this is, for example, is a beautiful event of the ones of this kind, of a candidate, if you like, for this kind of decay. Now, when you look at final states with 2 photons, there's many processes which can create 2 photons. And in fact, you can see there was a background. What you see here in red is what was being foreseen, sorry, in dashed red, was being foreseen as being the background one would see there. And then all of a sudden as well, in these specific channels, you started seeing an accumulation, if you like, an accumulation of additional events compared to what we were foreseeing. And it was exactly at the same mass. So basically, we were seeing the decay of the Higgs boson in 2 different channels at the same mass. And so basically, that's what really convinced us that we were seeing something serious. In fact, this thing was reported on July 4th, 2012, and we didn't manage to keep it quiet, in the sense that people were expecting there would be something. In fact, the auditorium door was closed until 8 o'clock in the morning, and you could see was at 10 p.m. the previous day, people sleeping in front of the door. By 7 p.m., you had a 300 meters line outside in the lawn at CERNE. In fact, I think probably only 20% of the people which were queuing managed to enter the auditorium that day. And you can see that this is the moment when basically the experiment had announced that we were above the 5 sigma significance, which was, if you like, telling that the probability that it was a fluctuation of the background was insignificant. And then you can see these are the guys. This is Guralnik and Egan. The only guy who was missing that day, well, there was Braut, who had died, and then Kibble didn't come. And you believe it or not, this was the first day since 1964 that Higgs and Englert met. So, after the 4th of July 2012, our table is basically richer, and it has 1 element more, which is the Higgs boson. The graviton is still out. Now, let me tell you as well that we are publishing a lot. We are doing a lot of measurements, so we are not only doing Higgs physics. And here is an example, if you like. We look at the production cross-sections with precisions, and also at an energy which was never done before, with precision which is unprecedented, of many different kind of particle production, WZ, pairs of bosons, in fact triple boson productions, top quark, top with the bosons, and these sort of things, and here is the Higgs. So this is just to give you an idea of the richness of the measurements which we do, and also not only measurement, but we are trying to look for anything else which we might not be seeing. For example, the searches are represented, the papers, number of papers on searches are represented by this yellow line, and you can see there is a lot of them going. And the one thing to be noticed is that we are basically publishing order of 150 scientific papers per year as a collaboration over the data. And so far we have published more than 400 papers. And typically we publish 2.5 papers per week. The size of the collaboration explains as well why we have this rate. We are 2,200 physicists from 187 institutes and 43 different countries. So this is a lot of effort being put into research. Now, let me point out one thing, the importance of precise measurements as well. Because basically, when you look at the equations and you try to put everything together, you can basically test the coherence of the theory. And for example, when you look at the W boson mass and the top quark mass, you basically, this is the measurement, if you like, representing also the errors on which we know the W boson mass and the top quark mass. And what you see here in blue is instead making the closure from the theoretical model, looking at all of the other measurements and what you would predict, including the Higgs boson, and what, looking at all the other measurements and what you would predict as the allowed area for the W boson mass and the top quark mass. You can see that basically the overlap is decent, but imagine that the error on the other measurement would shrink, and also the errors on the direct measurement of the W boson mass and top core mass would basically shrink, the thing becoming compatible, that would again mean a failure of our model, which also would mean that there is something which we have to add into the model in order to understand things better. This is the importance of precision measurements into our things. So where do we go from there? Oh, with the Higgs boson, which was basically, if you like, the thing we have been searching for 40 years, and we finally found it, we have laid the keystone of the standard model cathedral. Now, I've chosen on purpose some sort of fuzzy picture of a cathedral, because basically you can see that this picture could be improved. So what we will do, if you like now, is obviously we continue taking data, we increase the statistics, we increase the precisions. So what we will do is to get a better picture, so measure better the characteristic of the standard model. The question is this all we are left to do? Is this all which we can contribute from the accelerator physics point of view, the particle physics point of view, in understanding better how nature works? Now, it's not the first time that this issue is posed. There is a famous quote by Lord Kelvin in 1900, after they had, I think they had discovered just the electron, I mean the model of the atoms, seeing that there was an electron orbiting around something. So he said, there is nothing new to be discovered in physics now. All that remains is more and more precise measurements. So, well, history proved him wrong. Now let's see what we do. So, indeed, there is more. There are a lot of fundamental questions which still do not have an answer, where we believe we can contribute with particle physics and accelerators. The elephant in the quantum field theory room is being gravity. I mean, it's been difficult to reconcile quantum mechanics and gravity, and that has been a theoretical nightmare since 100 years. I think that the last 60 years of life was 50 years of life of Einstein we spent trying to do this without success. Dark matter is also another cloud in the standard model, and in fact I will basically concentrate more of my talk on this, because there's a very strong evidence for this, and we have actually no answer in explaining what dark matter is. And the some other fundamental question is why we have essentially only baryonic matter in our universe and not antibaryons. It's also another questions which we have no answer to, and which, for example, the experiment of Andrei Zia is trying to give an answer to. Now, there must be more than the standard model, in fact. For example, there are other questions which are a corollary to what we know today. Why 3 families of fundamental particles? Something which I didn't mention and I will not have the time to cover is that when you look at those funny particles which are called neutrinos, the structure of the neutrino sector is also not well understood. and it might be a signature of physics beyond the standard model, which is hidden, in fact, in the fact that the neutrino can transform into each other. The standard model itself seems to indicate that something is missing. In fact, when you try to calculate within the standard model the physical Higgs mass, it turns out that you have to tune the bare mass in the calculation to 1 part in 10 to the 32 in order to prevent it from basically jumping to the next mass which we know being in nature, which is the mass of the Planck mass, if you like, is the mass at which gravity becomes as strong as all of the other interactions, and so is identified by a Planck mass, which is in fact several orders of magnitude above the Higgs mass. So, in other words, this is possible. You can tune things like this, but imagine you have to do basically calculation to an incredible precision in order to be able to achieve that. It sounds unnatural to a certain extent. So, in other words, we have a beautiful cathedral with actually rather solid foundation, but when you start looking a little bit from a distance, you see something which is kind of odd. I mean, for which you don't have I hope you have all seen Avatar. Otherwise, you don't understand this picture. It's a beautiful movie anyway. You should look at it. So you can see there is something odd in here. If you look, just this is okay, but then there's something which is missing in the theoretical explanation of things. Indeed, this has been obvious for quite some time, that even if you had found the Higgs, could not be the end of the story, because there were too many unanswered questions and too many contradictions in the system, even though. And in fact, our friends, the theorists, have basically really released their imagination. Here is a subset of the various theories with their funny names of we call beyond the standard model theories. What we know today is the standard model, and then to go beyond, people have invented enormous amount of things. By the way, some corners of these pictures have already been excluded by the first data taken at the LHC. Now, this brings up an interesting sociological aspect of our world, which is basically a relation between experimentalists and theorists. In fact, when you look at things, I mean, this is when you ask a theorist how he sees himself compared to experimentalist, this represents it, right? So this is a theorist, this is an experimentalist. Now, it's actually a defendable picture, even though I'm an experimentalist and I resent it. But when you have very tight prediction, for example, in the last 40 years, we had the Higgs boson, which was a beacon to which we were looking at, and it was obvious that the theorist could feel authorized to think that, well, I told you what you to look for, and then you should look for it, and these sort of things. Now, today we found it, and they are completely confused, in the sense that they don't tell us really in which directions to go. So I think that this is the way the picture is seen by experimentalists. You see, these are the experiments, the LHC experiments, these are the theorists. And I think that this is the situation we are in now, where basically we have to tell them which is the right way to look at. Now let me try, it would be too much to try to cover all of the avenues for going beyond the standard model, but there's one thing which is firmly established, and I think, and it is the primary energy frontier objective today, and which is dark matter. Now, again, let me do some history here. Dark matter has been with us for a while. The first guy who actually hypothesized it as the name of dunkle materie is when looking at the galaxy in the Coma cluster, which on the edge of the Coma cluster, which were moving too rapidly around the thing. This is Fritz Zwicky in 1933. In fact, it can be considered the beginning of the dark matter mystery. It's also true that when you look at the guy, you understand why not everybody was believing him. Also, at the time, people were not sure, because the way the dark matter works is the fact that they look at the orbital speed of galaxies at the edge of a cluster of galaxy, and then they try to say, well, the only thing which determines their speed is like when you have an elastic with a ball, I mean a wire with a ball, and then the speed at which the ball goes depends on the force with which you hold it. Now, the force which is inside the cluster of galaxy is the sum of all of the mass of all of the galaxy, and so you make the mass of all of what you see, and that is the gravitational attraction, which basically conditions the speed of the galaxy. So, grosso modo, it's a little bit simplified, but it is luckily like this. Now, at the beginning, people felt, well, maybe there's an error in the calculation of all of the mass inside the cluster of galaxy, which was now. Those methods became more and more sophisticated. And in fact, I think it is with this lady that people really started believing that there was a serious problem. In fact, no matter how you were looking at it, how you were trying to explain things, these were different, if you like, models, the color things. And basically, the observation was this. And it was incompatible with an explanation which was based on just simply the matter which you could see, the atomic matter which basically shines or reflects light. I mean, the matter which we know. And that is why it's called dark matter, because basically it's something which does not interact with the regular matter, or if you like, doesn't interact with light. There's been much more sophisticated evidence recently, because in fact, there is this, the bullet cluster, there are two merging galaxies which are going through each other, and basically if you think about it, around the cluster, in the cluster of galaxies, there is matter, which is atomic matter, which is the intergalactic dust, which is the regular atomic matter which interacts with each other, and then you have also the dark matter. So basically, the matter which interact with each other, while the cluster goes through each other, they tend to slow down because they're interacting. While the dark matter, which doesn't interact, continues to accompany the galaxies. And you can see it here represented by computer. Is the blue one is the dark matter, the red one is the atomic matter. The atomic matter tends to basically lag behind because if they have interacted, they don't manage to follow the galaxy, and they provide some sort of fuzziness. They tend to obscure the stars which are behind, while the one which is accompany the galaxy tends, in fact, to be a lot of matter. It turns out they, in fact, provide gravitational lensing. You can see here these effects are the, if you like, the diffraction, gravitational diffraction of the light of the stars which are coming from behind. So, it turns out that when you do all of the calculation, I'm missing one slide here. When you do all the calculations, you have to introduce 5 times more matter than we see in order to explain all of these effects. So in other words, of the matter of the universe, we are able to see only 1/6. All of the rest is dark matter. It's actually a lot, and in fact, that brought people to do an interesting simulation. This was done by the supercomputer in San Diego. And it is, if you like, assuming that the only thing which represents the variety of structure which you see in our universe, the stars, the lumpiness of the universe, is coming from gravitational attraction. So basically you put all of this matter in, you let the universe expand over 14 billion years, and you see what happens. Whether you create a universe which has a lumpiness like what we know today. Or not. Now, it is an accelerated simulation. It's not going to last 14 billion years. And so this, if you like, is the movie is going to span 14... Sorry. The movie is going to span 14 billion years. And on this side is if you have only the atomic matter which we see today, and on this side is also if you have dark matter. Now you let it go through, and if you were to look at it carefully, you would see in details, I mean this is the whole size of the whole universe, so you don't have a big resolution here. But you would see that there is some structure here, but it is nowhere the night sky which we see. Now, this is no pretension of representing the universe as we see it, but on the other hand, you can see that this resembles the night sky as we see it today, while this is nowhere close. So in other words, in order to create the structure which is in the universe today as well, you need that much more matter than what we see. So I think that the evidence for dark matter is well established, and also one can see that it is extremely important that dark matter is there, otherwise we would not be there. How can we see dark matter? The way we can see it in our accelerators is basically by this kind of processes. Now this is, if you like, an instantiation of one of those theories which was being proposed. In fact, it's one of the most established one, which you might have heard about, which is called supersymmetry. And in supersymmetry, there is a whole zoo of new particles which are sitting at a mass which is much higher than what we see in the particles around us. That is why they're not common in our world today. But again, if you have enough energy in the accelerator, you can produce them. And once you produce them, I mean, all of the supersymmetric particles have this tilde on top. Now, these particles are unstable. There's only the final chain of decay as only one supersymmetric particle which is stable, which in fact is the candidate of dark matter. So if dark matter is formed by some sort of particle, and this particle is of this kind, we would be able to produce it. And in fact, the way it's not a simple thing, because you can see that what you naturally produced is something like a squark and this gluino, and then this thing tends to decay. Decay is always, there's possibly a complicated decay chain of other supersymmetric particles, which eventually always, if you like, the supersymmetricity is maintained. And so when they decay in supersymmetric particle and the regular particle. And the regular particle, like a quark, two quarks, an electron, a muon, maybe, we can see. This is what we measure in our detector. And what we measure in our detector is also, they are conceived such that if there is another particle, which is basically an escape, because this thing is, remember, is dark, it doesn't interact, it takes away energy. So it takes away energy, so we measure the energy which is missing from the event, and this would be one way, there are others, that we could discover dark matter is in this form. It will not be easy, but we have built our detectors to be able to do so. It's not the only way that dark matter can be found, because this is, if you like, is what we are looking is the production of dark matter. But you could have, you know, scattering of dark matter, just like billiard balls, with the material in a detector. This is typical experiments which are done underground, where you can basically detect the recoil of the proton which is being knocked off by the dark matter which is coming from from things. Again, this is going to be a very rare event, because these things do not really interact very much. Or you could, in fact, seeing the annihilation of dark matter into gamma ray astronomy, which would give rise typically, for example, to pairs of very high energy photons. So there is gamma ray astronomy, there is underground experiments of cosmic rays and accelerators, which could all build evidence for this dark matter. And there's more and more sophisticated experiments which are being built, not only in accelerators, to do so. So as I said, dark matter is one of the goals for the future. Now, the long-term future, let me conclude by telling you, I mean, the original LHC program was to deliver 300 inverse femtobarn. This is the unit of what you call luminosity. It's the unit, if you like, of data which is being delivered to the experiment. Today, just to give you an idea, they've delivered 30 inverse femtobarn. So the original program was that by the year 2021, one would have had delivered 10 times what they have delivered today. Now, in 2012, the CERN Council approved an extension of the program to allow accumulation of more than 3,000 inverse femtobarn. So if you like, 100 times what we have today in a 10-year period between 2025 and 2035. In fact, this also means that we will get an enormous amount of data, which will allow us to do very precise measurements. Now, this, if you like, is the outline on how as a function of here, the integrated amount of data which we will have. But there's one point here to be noticed, which is, in order to achieve this, you basically have to increase, if you like, the probability of having two protons which are basically colliding. Today, in 2012, we had an average of 20 collision per crossing of the beams. When we go there or there, we will have between 150 and 200 collisions. That makes very complicated pattern recognition. I'm sure that this is, I mean, you're familiar with this, in the sense that out of these 200 collisions, there's one which is the most interesting of all, and you would like to basically judge whether that one is something which can teach you something, because we cannot keep all of the collisions. The trivial ones we basically throw away. So that is one problem. And also it creates an enormous problem of radiation. I mean, there's enormous, I mean, all of these particles which are flying around is radiation, and we need to basically have to basically go through an upgrade program, because we know that certain part of our detector, like the central tracker and the forward calorimeter, will not be apt to take that amount of radiation. We'll have to replace them. So we are in a process of defining what our future is and defining our upgrades. And here, I mean, I will not go through the details here, but there's many different things which deal with trying to deal with the increase, if you like, rate of interactions to make sure that we have detectors which are able to take it. Now, just to give you an idea, what do we expect? I mean, it took 2 years to discover the Higgs boson. Will it take another just a couple of years? Remember that one thing I'm going to mention at a time. The LHC stopped for 2 years, and now it is restarted, in fact, 2 days ago, at an energy which is almost double the one before. So basically, we are opening a new energy frontier, E equal mc squared. The real name of the game is the energy which you put in the game. So if there is a new particle which has a mass which is accessible with this new energy, we will discover it. So we are all excited about that. So you might tell, well, are you going to announce the discovery in another couple of years? Maybe. Here is just to give you an idea, is that in supersymmetric models using this established, I would say rather well established from the mathematical point of view theory, which is supersymmetry, we have basically looked at 9 different experimental signatures with 5 different types of these models. These models are not as well defined as the standard model. You have parameters and you can span them. And here you can see what you expect in terms of having a 5 sigma discovery of supersymmetry, would be that there would be discovery of supersymmetry in these 5 models. Whether we would be able to discover it at the end of the established program, the 300 inverse femto, I mean 10 times more luminosity than today, or we will have to wait until the end of the full program in 2035. And you can see that there is a lot of them where you basically tend to discover them probably quickly. On the other hand, there is also the possibility that you'll have to wait for a long time to be able to reach a level of significance which tells you that you are not seeing a statistical fluctuation. So we cannot promise anything. Just to relate to something which you are very familiar with, one of the other challenges is the raw data size logged per year. To add to this, one has to actually add the process and the derived data, which can easily be as much, if not more. Now, here we are. This is the disk, the size is a petabyte. This is where we are today in terms of raw data. This is in terms of raw data accumulated per year. This is where we will be in 2025. So it gives you a measure of the challenges which we have in every field. Radiation hardness, rate for just taking this data, but as well processing this. I mean, this is going to be non-trivial CPU for getting them through. Well, let me conclude by just saying what I mentioned. The LHC has restarted. It is stopped for 2 years in order to go from an energy of 8 tera-electron volt to 13 tera-electron volt. And after more than 2 years, LHC has restarted, delivering collision at 13 TeV. And this is, in fact, the first event which we have seen. When was it? 2 days ago. I have now forgotten. It was an exciting day. And you can tell that the fact of seeing this sort of porcupine kind of thing basically meant that everything was working. And so we had been working for 2 years as well, doing things, changing things around. And so you can tell that we were very happy. There was one colleague which actually caught this moment. And this is a nice picture, which is basically in every website, media website these days. In summary, accelerator-based particle physics has again achieved a major success. I'm thinking about the Higgs boson. And experimental measurements are now taking center stage. We really need to go beyond the very successful standard model theory, but we lack a theoretical beacon like the Higgs boson has been in the past. The answer to some, we hope to most, of the most pressing unanswered puzzles could be indeed in the elementary particle domain. And hopefully, if nature is kind with us, we shall know in the next few years. So you should stay posted, and maybe we come back for another seminar in a few years' time. Thank you.
I will translate how this data can be compressed, and what is the lifetime of this data? How long this data should be stored for?
So we have some compression mechanism. The raw data size as it comes out of the detector is between 1 and 1.5 megabytes. By the time we basically store it, we reduce the size by roughly 1/3 because there is a lot of empty channels. Our detector is like a camera which has 80 million channels. So if you like, it's an 80 megabit channel camera which takes data at 40 megahertz. So these are compressed. In fact, to a certain extent, the raw data sometimes is smaller than actually the data which we reconstruct, because then the data is passed through computer programs which basically tend to reconstruct all of the physics objects which are in the data. Tracks, leptons, photons, hadronic showers, muons, and things like that. Now, the lifetime of it. The lifetime, and this data then is stored at least twice, to have redundancy. In one of the, we have roughly 60 computer centers around the world which are on the grid, which are basically catering to our experiment. So this is stored, and we have committed, in fact, to make this data public. So, in other words, as part of this agreement for making the data public, there's a lot of resources which are also invested by places like, NSF in the United States, European Community in Europe. The assumption is this data will be living forever. So it will be kept forever. So on the other hand, it is kept on disks at this moment in our computer centers. And we basically have agreed that we would make it public once we feel that we have exploited it. Just to give you an idea, we have made public the 2010 data set last year. So it took roughly 4 years for us to judge that we as a collaboration had no more use, had no more reasons to exploit this data. So this gives you an idea on the time between when we take data and when the data will become public and available everywhere. Our software is open source, and it is available, and the data is going. We have committed to that. And as I said, the assumption is that someone is going to pay to keep it forever, not us.
I will try to translate, but I'm not sure I understand the question.
Unique is all trace unique. Always some group, some abstraction.
You mean the reconstruction of what we do, those trajectories? Well, it's a complex thing, because basically some of them are extremely well measured. There are tracks of different quality. Most of them are extremely well measured, and they are unique. Others have a level where they could have shared the 2 hits, because they are a single hit which could belong to 2 tracks, and this basically defines a class of tracks which people can use or not use. It's a matter of analysis afterwards. But in principle, we have a representation of the event, if you like, of the picture, which is unique, and people can use it. We also tend to save those cases where there was an ambiguity at the level of the reconstruction, which people can try to use if they want to see that if there is alternative interpretation of the event. No, it's not stochastic. It's somewhat deterministic. The randomness can happen in the way the events manifest itself. If there are two tracks very close to each other, they could be, you know, the way you measure a point on a track has a precision typically of 7 to 10 micron. And if two tracks extrapolate to the same 2 or 3 sigma of the 10 to the 20, 30 micron, you don't know to which track to assign that hit, and so you basically you understand what I mean. You tend to assign it to both, and you give the choice to whoever does the analysis to.
Извините, пожалуйста, прошу прощения. Я думаю, что вы потом это обсудите с лектором, потому что есть еще вопросы, и у нас идет запись трансляции. Мы принимаем только в микрофон. Спасибо. Коллеги, еще вопросы?
No, I think I understand. So you want to leave room to someone else to ask questions, right?
Kind of that, yeah. Just a second. Спасибо, Андрей.
Thank you for such a good presentation. It was very interesting. I have a question. As I understand, there are a lot of theories which try to improve standard theory, and they often make predictions about particles with very high masses which we cannot achieve in modern acceleration. What are we going to do if we will not find any evidence in energy levels we can achieve with our capabilities now?
Very good question. The point is that it's a very good question, because basically, first of all, the theorists who basically predict particles which cannot be seen are very wise theorists, in the sense that their theories cannot be disproved. So it's a sort of virtual theory. But apart from these jokes, it's true. There are a lot of theories which go beyond the standard model. They tend to explain these unexplained questions, and basically do not have any predictions on things which we can measure directly. There is the ultimate handle which we have is precision. If you like, one thing which I can show is this one. You can basically, from all of the measurement which you do, if you like, you can predict what to expect for something which you can measure rather precisely. And if this prediction differs from what you are measuring, you might have an indication on which way you want to go. It's not guaranteed, but that is if you like, is the indirect way of figuring out that there must be something, because that is the other thing. You could think, well, the fact of saying that what we have discovered, everything which was there to discover, and then the other stuff, there is, for example, a theory which says that which is somewhat anthropomorphic. There's a theory which says that of all the possible, that basically one could have a multiverse, that essentially the universe could be something which started off in a multitude of universes which are evolving, even with you know, which are evolving independently, and which have different laws of nature and things like that. And the one of all of the many multiverse, we are living in the one which has specifically these parameters as being set from the very beginning as being the thing which we are asking ourselves as being a question. And the only reason why it is like there is because we are there to observe it. Okay, that is as well difficult to prove, but it is a possibility. So there is a possibility that really there is no. We cannot understand more than the universe is as it is, and be done. Now there's some questions which probably still require answers. On the other hand, if you basically see that inconsistency inside your model by trying to make a closure, if you like. You abstract a couple of parameters and you try to predict these parameters from everything else which you measure, and you see that these things becomes incompatible. Then you might have, first of all, you know that there is something which you are not understanding, and there must be some other theory. The theory must be extended, and it might give you indications on which way to extend it, even though you have no direct evidence of measuring a specific new particle. You want to say something,
Yeah,
Andrea?
could you go back to the 24, by one slide back? Right. So, no, this number of papers as a function of time.
Yeah.
In fact, when we are looking for beyond the standard model, physics is just these yellow papers, right, which are on the top.
Yes.
And obviously, looking at this picture, that people were mostly motivated by looking for the exotics, for the physics beyond the standard model. What strikes me here, there is a period of reduced activity right after Higgs discovery, right? Because in the year of from January 2013 up to 2014, there was single paper.
Yes.
So people were so happy with the discovery of the Higgs, which perfectly confirmed standard model, that they decided to stop, right? And then there is another.
No, I can tell you what it is.
Please.
Each one of these lines corresponds to what internally we are organized, our research is organized in terms of physics analysis groups. Okay? And you have the exotic physics analysis group, you have the the SUSY supersymmetry, you have the B physics and these other things. Now it turns out that in exotic and in Higgs, where is Higgs? Higgs is this one. Higgs is this one, which is well flattened out. In exotic and Higgs, we are 2,200, there were something like 1,500 between these two groups. So basically, it means that there were an enormous amount of students which basically finished their thesis with this thing, while all of the other very serious groups which were doing measurements, which take longer, if you like. Yeah.
Thank you again for the talk. Question about what could be like next Higgs boson. I mean, the target that's set by theory, and that can be measured in real existing collider. So what you think in this set of modern theories can set the next target?
The next target. Well, as you can imagine, the target which we prefer is from those theorists which basically predict particles which we can see.
Yes.
So one example which I was giving you here is in fact the thing which we would be seeing first. If this were real, if the gluino mass is reachable, meaning below 2 tera-electron volts, just to give you an idea, is reachable, we will discover it in the next 2 years. Okay, so this is a nice target. If the gluino mass instead is unreachable and the only thing which could be produced are quarks, that is going to take a little bit longer, but still fast. If instead the only thing which could be produced directly is a pair of these two guys, you might have to wait for another 5 to 7 years, always assuming that any of these particles, you see there's a cascade which is was chosen as a very favorable thing, because it means that we could produce gluinos, we could produce quarks, which basically, and the gluino would basically be heavier than this Chi-02, which, if you like, is the heavy brother of the Chi-01, which is the lightest, but there's also leptons here. So basically, it would mean that if we can produce this, we can produce all of the others. That would be the dream scenario, in the sense that we will basically cover almost the whole zoo of supersymmetric particles. at this moment, we would be very happy if there is certain theoretical parameters, even of supersymmetry, which basically foresees that there might be, for some accident of the parameter space, there might be one of these particles which is reachable by us, while all of the others are maybe much, much heavier. And so we would even be happy with this kind of scenario. So there's plenty. Now, what we are concentrating on is supersymmetry, because supersymmetry, if you like, is the most established theory which would regularize, if you like, something which I just touched upon, which is this problem. The fact of having to tune calculations to one part in 10 to the 32 is considered by everybody unnatural, or if you want to use a different term, is ugly. Beauty has always been a heuristic way of looking at theories. I mean, everybody gets excited if a theory looks beautiful in mathematical terms. This thing is as ugly as it can be. So it's fine-tuned. It's very fine-tuned. There are other things in nature which are fine-tuned, but they are fine-tuned at 1 part in 10 to the 4, not in 1 part in 10 to the 32. So, fine. The point is that if supersymmetry were to be the right extension, if you like, to understand the way the universe works, it would basically solve this problem in a very beautiful way. And so that is what people are concentrating on. It's also because it's only natural. You can do calculation, you can have simulations of various different spectra of possible supersymmetric particle, which you can simulate to your detector, so you know exactly how it looks like. And so it's the same process which we did with the Higgs. You look what to look for in terms of topologies of final states, and so it's very easy. In fact, a discussion we were having today about machine learning and these sort of things, the thing which we are paranoid about is, given that, as I don't know if I told you, out of the, I said that we are taking 80 megabit pictures at 40 megahertz. You think about it, I'm sure the first thing you realize that we cannot store all of this stuff. So basically we do a selection of these events, which is only, eventually we keep only 1 kilohertz of the 40 megahertz. And we have a whole software which does a reconstruction of the thing and tries to find topologies of events which do not correspond to something which we expect, in some sense, trying to measure something new. The real point is that something new means it's something which is different from what we know. And the way we are typically driven is a rather old-fashioned way, which is basically being driven by the possible extension which our theorist friends tell us, and then we look for these topologies that they predict. Nobody might have predicted the right theory, so there might be something out there which is different from what we know, and which we might be missing because simply we throw it away because we don't trigger on it. We don't select it to put it on disk to be looked at it more carefully later. So that is one aspect, for example, of, I would say, unbiased machine learning that we would like to exploit, or which people are actually trying very hard to understand. I mean, you are more advanced than our guys, but we try as well to.
Is it already running in the run 2? I mean, this kind of algorithm.
No.
For selecting.
Well, we are trying to look in an unbiased way for something which you would really consider very different. I mean, the concept of very different from what you expect, it's already there. Like, for example, if you see an event which has a multiplicity larger than 5 or 6 muons, you know that this is kind of fairly rare and these other things, but it's not systematic. It's not systematic. In fact, all of the effort on the machine learning side is going in the direction of trying to be a little bit more systematic than this.
Tiziano,
yeah.
Thank you for your nice talk. May I ask you a little bit politically incorrect question? How would you motivate bright undergraduate student why he or she should join you and not Atlas.
Oh no, but that is
or
easy.
PhD.
No. As in not Atlas because we are better, but that is.
Then the next question: what is your subjective view of the main advantages of CMS over Atlas and disadvantages?
I think. Well, no. Is it recorded? No. Now, also let me not express my personal impression, but let me quote, because there is obviously young people from Atlas which comes to CMS, and vice versa, young people from CMS that after graduation get hired by Atlas universities. So I think that the two things which are considered better in CMS than in Atlas are: we have an easier software environment to get started with. We have, for example, I've had since the very beginning, we have designed classes for people who know the thing with root, which are self-described. So you have a description, if you like, an intrinsic description of the classes of physics object elements which you have, which is implicit into the data. Atlas went through a so-called revolution during the long shutdown, which is finished, in order to introduce partially this. So this is one. Our software is much more efficient than the one of Atlas. To give you an idea, we are quicker, measured by the publication rate. We are quicker in reaching a result than Atlas, and Atlas basically uses almost twice as much the computing power that we have around the world. I mean, we integrate over the whole grid. It's also true that our guys are typically doing analysis. This moment, for example, for the start of the data which we are starting to take, we are basically in the process, and we will be finished soon, to generate 2 billion events of generated data, fully generated data. I think in Atlas they are at the level of providing these guys half a billion. So these are, if you like, software performance things. The other thing is that I'm told that we are a lot less formal in Atlas. Well, we have 2,200 instead of 2,800, so it's not so much smaller, so it's still above threshold. But so we are a huge organization, and we have 3 levels of hierarchy in the thing. On the other end, when it comes to discussion for analysis, or if you like, the approval process for analysis and things like that, we are much leaner than they are. That's what I'm told. And on the other end, I should say as well what is the criticism which is made towards CMS. We are being told that we are, for some reason it seems to be contradictory, we are less social. In the sense that we seem to not to organize socially. No. You know, for example, their meetings are much better attended than ours. And we don't understand why, because they have even more meetings. Our young people are making a joke about CMS name, which is called Continuous Meeting Society. And when you look at Indicom, this tool which we use to schedule meetings, they have at least 30% more meetings than we have. And in their case, apparently the meetings are better attended than ours. In our case, sometimes we have a problem in justifying the level of meeting which we are having, because in certain cases the attendance is rather poor. On the other hand, the slides which are being presented are used as reference in many cases, even for the career of people. So I have only to say this. I mean, I don't understand it completely. This aspect of somehow Atlas seems to aggregate communities better than we do, which I take it as an area which could improve, not to have more meeting.
Thank you for your talk. And my question about machine learning. So on which state do you use machine learning? For example, in LHCb we use machine learning in trigger system. So not cut-based analysis, but truly machine learning. And for example, in Atlas they used 128 cuts to pre-select data and to store them into memory. So what about CMS?
Okay, I don't know whether what you call cuts means trigger configuration.
Kind of condition written.
Trigger condition. Well, because if you use cuts is a negative thing. Trigger conditions basically are really aiming to select specific topology. So in CMS, the only reason why they use 128 is because they've designed their electronics to be able to take only 128. In CMS, we are proud that we have 420. Because our electronics allows it. In fact, it is one of the reasons why we could do the BS into mu analysis, which was that we could dedicate, and in fact, every single trigger is allocated a specific bandwidth. That's okay, but we also reserve 30 years of log data to this specific analysis. Well, it would be hopeless, maybe, but this is not true.
Right, I understand that.
No, but the point is that to address your questions, I think so. I don't consider the fact that one has many different triggers as negative. What I consider negative is that we don't have any machine learning applied to trigger yet. So to answer the question, it's not. But as I say, there are at least 2 groups which are very active on it, and there is a global attempt. In fact, promoted by our guys, you know Maurizio Pierini is actually trying to organize a machine learning workshop at CERNE in the fall.